So we'll take up atomic structure, the basic concepts, right? In 1808, John Dalton was the first person to give a theory called atomic theory of matter, in which he told matter has atoms. Okay, so John Dalton in 1808, in the beginning of 19th century. Okay, so then only he by then everybody were surprised to know uh, the atom word introduced by John Dalton. Okay, before that there was no idea at all. So what this matter exists, what it exactly contains, all those things, right? So John Dalton only told what is the theory called atomic theory of matter. Atomic theory of matter. Now, as per this concept, atomic theory of matter, so matter is made up of matter is made of no small, indivisible. Every word is a definition of atom by then. Okay, small, indivisible. Okay, invisible particle called atom. Particle called atom. And different elements will have different atoms. And of course, this theory you are going to study in some basic concepts of chemistry also. And different atoms of different elements undergo chemical combination to form compounds, all those things. He briefly explained about atoms and its properties. But whatever he has given, indivisible, invisible concept, now if you look back into the theory of atomic theory of matter, this indivisible, it is divisible now. Invisible, atom can be at least seen in the indirect means, by indirect means. Okay, so as of now the concept is atom is divisible. Atom is divisible and atom is invisible. What he told, no, it is visible. Okay, can be visualized at least by indirect methods. Okay, so the concept which has been given, only word is remaining. That's all. Whatever the word given, atom is remaining. Rest everything has been changed, right? So the concept of atom is quite different now. As I was telling, as you go deeper into the atom, there is more to explore. There is another universe inside in an atom. Okay, as you go outside, exploring universe is so magnanimous and so huge, like that. Even in tiniest particle, that is atom, inside there is another universe to unfold. Now, to start with, when John Dalton gave atomic theory of matter, for quite a long time, people were believing that is the correct theory, and because he was highly influential and all. Then J.J. Thomson has done some discharge tube experiment. Discharge tube.
ಮನೆಯವ್ರು ಸ್ನಾನ ಮಾಡಕ್ 3 ಗಂಟೆಗೆ ಅವನಾರ ಎದೊಳ್ತಾನ.
Mute ಮಾಡ್ಕೋಪ. All of you have to mute whenever you want to speak with me, not with others. You can unmute. So J.J. Thomson, discharge tube experiment. In this experiment, he discovers electrons. It discovers electrons. And electrons, negatively charged particles. Okay. Later, mass and charge, everything was determined. Okay. After that, another scientist by name Goldstein. The idea was if matter contains some negative particles, then it should contain positive particle also. How come positive particle? Because any matter that exists in the nature should be neutral. If negative particle is there, there should be positive also. Thinking that the same discharge tube experiment has been done with slight modifications. They took perforated anode, then they got anode rays. This is cathode ray experiments. Based on that, electrons were discovered. Here, anode ray. Okay, so here protons were discovered. So this is discovery of protons. Protons were proven to be positive particles. Okay, right. Next, a scientist by name James Chadwick. He was doing some bombardment experiment. He was hitting beryllium. Okay, for it is 9 with alpha particle. Alpha particle means it is nothing but helium nucleus, 2He4 we write. Okay, 4 beryllium 9, 2He4. When this alpha particle bombards, hits the beryllium, then nucleus of beryllium changes to carbon. Actually, 6, it becomes 12. And if you take the difference, 4 plus 2, 6, 9 plus 4, 13. So that means the difference in mass number of 1 has to be seen here. So one particle of 0 charge and 1 mass is liberated. This indicates 0 charge and mass number 1, right? And these particles which were emitted along with carbon were passed through electric field. They neither deflected towards anode nor towards cathode. Since they were having no charge, they were not deflected. So therefore, they were called as neutral neutrons. So neutron discovery has taken place by James Chadwick. So almost a century. These are all the experiments which almost took place in the beginning of 20th century and atomic theory of matter in the beginning of 19th century. So after that, people were started thinking if these particles are there inside the atom is not indivisible, rather it is divisible. It is made up of some other fundamental particles. So these electron, proton, neutrons were called as fundamental particles. Okay. Fundamental particles, and their charge and mass has been determined. Charge, mass. And now you need to know these values: charge, mass, and mass. Okay. When you say electron, what is the symbol of electron? We say E. Can anybody tell me what is the charge on electron? What is the charge on electron?
-1.
We say it has 1 unit of negative charge, but it has some magnitude, some value. That is what I'm asking. What is the magnitude of charge on electron?
The 1.6 into 10 raise something. Is that correct?
1.602 into 10 raised
into 10 to the power of -19.
Coulomb charge is measured in coulombs. And proton mass charge is equal in magnitude, that is 1.602 into 10 raised to -19 coulomb, but opposite in sign, it is plus. Okay, so this amount of magnitude of negative charge is considered as 1 unit minus 1 unit of negative charge, minus 1. This is plus 1 unit of positive charge. If I write sodium plus Na plus ion, there is 1 unit of positive charge which is equal to this magnitude. If I write Cl minus ion, minus 1 unit is in excess. This much magnitude of negative charge will be there. That's me. What is the charge on neutron now? 0.
0.
Zero.
Then mass of electron, it is highly negligible. It is of the order of 9.1 into 10 raised to minus 31 kg. How much is this? 1.672 into 10 raised to minus 27 kg. And mass of neutron is almost comparable to proton, with a slight difference, 1.675 into 10 raised to minus 27 kg. Okay, so these are the three particles and their fundamental properties, charge and mass. You should remember in problems and all, they may not give you the value. Okay, you should remember. Okay. So this is the electron, proton, neutron in brief. After that, the question that definitely arises is how these particles have been arranged inside the atom. So the question was about structure of atom, and people started giving different structure. Mr. J.J. Thomson has given one basic fundamental model, that is Thomson's plum pudding model. Thomson plum pudding model. That means he just compared the atom to be similar to a plum cake, okay, where the entire mass is of that of positive charge is the mass of the cake, which is uniformly distributed. Mass is uniformly distributed. Okay, throughout the atom. And if the mass of the entire plum cake is of positive charges, then there are electrons embedded there. Okay, there are electrons embedded in huge numbers here and there, which is nothing but the fruits that is seen in plum cake, like that. Okay, so these are all electrons. Oh. Okay, 1 second. I'll just. I think I need to switch off my video. Otherwise, this OneNote requires a lot of bandwidth. 1 second, it's commencing. Suddenly crashes here. Can you see the screen now? All of you?
Yes, sir.
I'll switch off my video. So this is uniformly distributed mass, that is positive, and these electrons are embedded with to balance the positive charges. Okay, to balance the positive charge, total positive charge, so that any atom is electrically neutral. Okay, this was a very basic one. This was neither explaining any of the properties nor accounting for some of the basic structures also. But later, a scientist by name Rutherford has conducted an experiment called alpha ray scattering experiment. Alpha ray scattering experiment. This is one of the important significant experiment which led to a new structure of atom. Now, if we think of a structure of atom, nucleus is there at the center, electron is revolving around the nucleus in different orbits. That basic idea of atom is basically given by Rutherford alpha ray scattering experiment. Okay, what did he do? What Mr. Rutherford has done? He took radioactive element radium. So what is radioactive element? A radioactive element is one which is unstable, which starts emitting radiations of high energy such as alpha ray, gamma ray, beta ray, like that. And while emitting such rays, those elements transform into other nuclei. Okay. For example, uranium, thorium, neptunium, they are all radioactive elements. So now he took radium. Radium is radioactive, no? So it has to be kept in a stable atmosphere. So he took lead, a lead block. Lead is stable, it is very stable towards radioactivity. And now radium has been taken in. This radium emits high energy radiation such as alpha ray, beta ray, and all. Now we want alpha rays. See, the rays which are emitted from this radium is passed through a slit to narrow down the beam. Okay, we need to get a narrow beam of radiation. So we are going to pass it through this slit. After that, these rays will be made to bombard the thin gold foil. A thin gold foil. Foil means a small sheet, that's all, a very thin sheet, gold foil. This is slit, and that is radium. Okay. Now, when alpha rays pass like this, there are plenty of alpha rays, right? They pass like that. They bombard gold foil. After bombardment, they may be transmitted directly, or some of them are found even scattered also. So to observe whether they are transmitting directly or getting scattered, there is one more arrangement here. So that is, there is some photosensitive screen which will be used. Okay, photosensitive. So this photosensitive screen is of the material called zinc sulfide. This is zinc sulfide screen. It is fluorescent screens. Fluorescent screen. That means alpha rays are energy particles, right? When they come and hit the fluorescent screen, like this, and they emit some light flashes, we say scintillations, light flashes or scintillations. For every alpha particle that hits this zinc sulfide screen, one light flash will be given. So number of light flashes which are emitted from the screen indicates alpha particles which are bombarding the screen. Is that okay? So it emits light flashes, or it produces light flashes when alpha ray bombards the screen. Is it okay? Now alpha rays are coming, it is narrowed down by the slit, then it will hit the gold foil. Some of the alpha particle will cross the gold foil and go straight and hit here. Now by the experiment it's been found out that maximum scintillations are obtained only here, right? Many scintillations, plenty scintillations were found, and some of them were being produced at an angle also, somewhere here like this. Some scintillations were produced here. That means light flashes. So few scintillations were observed at a large angle like this. And this is a movable zinc sulfide screen actually. If it is moved backward like this, after a while you can cut off passing alpha rays and pass it or push it backward like this. When the screen was pushed backward, very rarely scintillations were observed here backside also. So it is quite natural that alpha rays will hit and cross this and hit the zinc sulfide screen. But few scintillations or light flashes were observed behind the gold foil also. These were the observations of the experiment. What are the observations? Most of the scintillations, light flashes were obtained straight. Few were obtained at angles, and very, very few. It is almost 1 in 20,000 we say, or 1 in 10,000. So scintillations were produced even behind the gold foil also. So based on the observations made experimentally, he concludes conclusions. Okay. Why most of the alpha particles are hitting at the same point straight? So probably atom is empty space. Atom has empty space. Okay, and that's why alpha particles are going straight, and very few particles were deflected by large angles. So based on that, he concludes. See, alpha particle is also positive actually. It is similar to helium nucleus, I told you. So it has 2 units of positive charge. So when few alpha particles being positive are deflected, then he assumed that there is centrally located mass which is positive in the atom like that. Okay, he concluded like that. And very few particle, 1 in 20,000 retrace the path back. So that's because the mass is heavy. The mass is heavy, so that alpha particle whichever hits that mass, and it will be retraced back. Okay, the mass is heavy and occupy a small portion. Small portion in the atom. These were the conclusions based on the observations, and combining all this, he gives atomic model. Okay, the atomic model. According to him, the atom contains, okay, centrally located massive means having high mass. Entire mass of the atom, he says, is concentrated at the center. Okay, centrally located massive positively charged portion called nucleus. I can't write only, man. So he says centrally located massive positively charged portion is there in the atom. That's called nucleus. And Mr. Rutherford is the first person who to coin this nucleus concept. Okay. So now, second postulate says electrons are revolving around nucleus in different orbits or nothing but shells around the nucleus. Okay. So this is such that total electrical neutrality is maintained. So the charge on proton will be balanced by charge on electron. Charge on electrons. Okay. So this is how exactly the theory has been proposed. So based on that, whatever you assume the atom, so this is the nucleus now, which is having positive charges, and electrons are revolving around the nucleus in different shells or orbits. So those electrons are revolving. This is the assumption. It goes like that. So these are the electrons revolving in different. So this basic structure, even now, when we think of atom, it comes like this only, right? Nucleus and all. Of course, the new quantum mechanical model of an atom is highly complex and quite different. Okay, not to worry. This basic structure of an atom is still prevailing in all our perceptions, right, of an atom. With this structure, though he gave a remarkably different realistic structure of atom, but he failed in some of the aspects. See, always in scientific field, whenever a scientist proposes a theory about any aspect, that theory should also explain associated properties. be it physical property or chemical property. Now, Rutherford has proposed the model of an atom. Then the Rutherford has to explain all the properties of the atom. By then, the hydrogen spectrum was obtained and the different spectrum of various substances were known. Okay, people started questioning, if this is the correct structure of an atom, then how come the spectrum of atom can be obtained? Why the light is emitted from an atom? So some of the limitations include okay, the theory couldn't account for the spectrum. Account or explain anything. Account the spectrum of atom. Okay. Secondly, important limitations come from the stability. Okay. So didn't explain the stability. Stability of atom, which is quite important. What is the thing about this stability? Why the theory didn't explain the stability? See, according to Maxwell's theory of electromagnetic radiation, this nucleus, different orbits of electron. If electron is revolving around the nucleus, electron is charged particle. Okay. So according to Maxwell's theory, any charged particle when moves will liberate energy. Okay. Any moving charged particle must liberate energy. And he has demonstrated the electromagnetic radiations can be emitted from any moving charged particle. He has demonstrated. If that is true, then electron being charged particle which is revolving around the nucleus must also emit energy. If electron emits energy, it cannot stay in a particular orbit because it loses the energy, its kinetic energy, everything decreases. So finally it makes a spiral path like this and falls into the nucleus. Okay. If electron falls into the nucleus, atom will be not existing. It becomes completely destructed. Atom is there because electrons are there revolving around the nucleus. If atom falls into the nucleus, there is no atom, there is no universe. So on the other hand, atom is quite stable. The theory or Rutherford model did not explain the stability aspect at all. Why electron doesn't fall into the nucleus? Why does it remain in different orbits completely stable? So the theory did not explain. So this is Rutherford theory. There comes the complete failure of the theory with the drawback of the stability concept. Later, another significant theory has been proposed by Niels Bohr. Bohr's atomic model, we say. Bohr happened to be the student of Rutherford. He improvises the theory and gives a postulates of atomic model such that it overcomes all these flaws of Rutherford. Now, in this chapter, understanding Bohr's theory and its application is one of the important concepts. After Bohr's theory and its application, we have other part of it, okay, like quantum numbers, electronic configuration, rules for it, Heisenberg uncertainty principle, de Broglie's wave, all these things we have after Bohr's theory. So till Bohr's theory, it is one part. After Bohr's theory, it can be considered as another part of atomic structure. Now, to understand Niels Bohr theory of atom and its applications, we need to understand some of the important basic properties of atoms. Now, what we do after this Rutherford, will not take Bohr's theory. Instead, we'll consider all the basic properties, understand in brief, and then go to Bohr's theory. Is it okay? So now we'll take up some of the important fundamental concepts of atom and some of the properties. Okay. To start with this, you must know, this is atomic number. Atomic number generally represented as Z, atomic number Z. What is atomic number? What is atomic number?
The number of electrons and protons present in the atom.
It is not number of electrons and electrons
Or-
or protons. So it is basically, you should better define it in terms of only protons. So atomic number is number of protons in the nucleus of an atom. Number of protons in the nucleus of an atom. And of course, we know atom is neutral. So number of protons must be equal to number of electrons. So for an atom, you can say atomic number is equal to even number of electrons also, but not for ions always. Okay. For ions, number of electrons will be different, whereas proton number will be intact. It will be same. Okay. And now, atomic number is nothing but number of protons inside the nucleus of an atom. So define atomic number in terms of proton better, not in terms of electrons. Okay. Then we have something called mass number. Mass number A. Mass number is nothing but A is nothing but number of protons plus
neutrons.
number of neutrons. So the particles which are present inside the nucleus are called nucleons. So number of nucleons is mass number approximately, you can say that. So number of protons plus number of neutrons is what is mass number A. So next, symbol of an element. Generally, how do we represent a element? If X is the element, its atomic number will be written on the left hand side as a subscript, and its mass number will be written as a superscript, or it may be also will be written to the right hand superscript like this. No problem. For example, when you take carbon atomic number is 6, its mass number is 12. Okay. Uranium 92, uranium 236. Okay. So this is how exactly we represent the element symbol. However, this symbol particularly represents composition of nucleus, not the electron. Of course, you can extrapolate, that's all. For example, this lower number indicates atomic number of protons. And this is 12 mass number indicates number of neutrons and protons. So where is electrons? We just need to say proton number is equal to electron number. So we need not to worry about it. So it also gives electron number in an atom, not the ion. So how do you find number of neutrons? Number of neutrons, n is equal to, it is always A minus Z. A minus Z. Correct, no? So for example, number of neutrons here in case of carbon 12, we just write carbon 12 isotope. Neutron is equal to 12 minus 6 is equal to 6. And in case of uranium 236, number of neutrons is equal to 236 minus 92. 136 plus 8 you can do. It is 144. Okay, right. So this is number of, like that you can calculate number of neutrons in any atom. Fine. I was telling about atom is electrically neutral. Totally number of protons must be equal to number of electrons. Number of protons must be equal to number of electrons. But in case of ions, number of electrons will be different. So I just want to take up this ions. Tell me, how would you get ions from an atom? Or what are ions basically? Ions means what?
Charged particles.
Charged particles. So how do you get ions from atoms?
Sir, when
Sir,
atoms
when-
lose electrons.
Either by adding electrons to the
Or
atom
losing electrons.
or removing electrons from the atom. Okay. So ions are charged particles. Or better word is species. Okay. Charged particles. So they are obtained by adding or removing electrons from an atom. Correct? Like for example, some atom A is there. Okay, atom A is there. I'm going to add electron. Now it becomes negative ion or positive ion. A is
Negative.
there. I'm going to add an electron. It becomes negative ion or
Negative.
positive? Negative. It becomes A minus. A negative ion is called anion. In the anion, number of electrons will be greater than number of protons. Always in an atom, number of electrons will be equal to number of protons. That's why it will be neutral. I'm going to remove electron from this. Minus E. Remove electron. Now A becomes what?
Positive.
A plus, and it is a positive ion. A positive ion is called cation. And in cation, number of electrons will be less than number of protons. Okay, so this is how exactly it works. So this is cation. For example, now when I write some of the examples like the Na plus one, I say that Na plus has lost electron or gained electron when compared to atom.
Gained.
Na plus
Sir, lost.
lost cation. That plus one indicates has one electron less in comparison or with respect to Na atom. Okay, Na atom. For example, O2 minus has gained electron or lost electron?
Gained.
How many electrons?
2.
2.
So has 2 electrons excess with respect to O atom. So number of negative charges indicates how many electrons are excess. Number of positive charges indicate how many electrons are less. So that is basic knowledge required. Fine. So we have seen atomic number, mass number, and how to calculate neutron, that is A minus Z, and what is ions and all those things. Next, we'll take up something called isotopes. Isotopes. So these are the atoms of same element. These are the atoms of same element. When I say atoms of same element, atomic number must be same because there are 118 elements in the nature. Each element will have its own atomic number. So an element is defined by atomic number. Meaning if atomic number changes, element also changes. If atomic number 6 is there, it is always representing carbon. If atomic number changes to 7, it can never be carbon, it is nitrogen. If it changes to 8, it is oxygen. So every element is defined, characterized by its atomic number. Okay. So isotopes are atoms of same element. The same element means atomic number must be same. So with the same atomic number but different mass number, we say different mass number. Okay, so atoms of same element with same atomic number but different mass number, or you can say with the same proton number but different neutron number. Okay, because if atomic number is same and mass number is different, then proton number will be same, neutron number will be different, like that. No, both. We take some examples. The carbon has, in the nature, carbon exists in different isotopic forms. Okay, so what are the different isotopes? Carbon exists as 12, 13, and 14. What is the speciality of this carbon 14? Anybody? Carbon 14 is very special.
So
What
it can be used to find out how old an organism is
Very
for
good.
a fossil.
So exactly, carbon 14 is used in carbon dating. We say dating is not the normal meaning that we have. We go for a date, not that. So carbon dating is finding out the date of a fossil or an artifact. Okay, you are excavating the earth crust. Suddenly you get some kind of huge bones. Okay, of an animal or a person or something like that. Then immediately you subject it for carbon because it is radioactive. It will be emitting some radiations. You will be knowing about half-life of radioactive elements. From that data, how many radiations are being emitted now in that sample which is excavated from the earth crust. So from that they compare and find out approximate, not exactly in terms of days and seconds you will not get. So approximate age will be okay. So it may be they say 500,000 years or 500 years, 250 years or thousands of years. All these things because of carbon dating. Okay, right. So like that, hydrogen exists in its three different isotopic forms. Most stable, even in carbon, among the three isotopes, carbon 12 is most stable. One form will be most stable on this. It is abundant and most stable. Like that, in case of hydrogen, it is 1H1, 1H2, 1H3, and the three isotopes have different names. This is protium, and this is deuterium. We also call it as heavy hydrogen. This is tritium. 1H3 is tritium. So protium, deuterium, tritium. So these are the things. Like that, most of the elements exhibit in or exist in the nature in their isotopic form. Of all the isotopes, one will be most stable. That will be most abundant also in the nature. Okay. Whichever is stable, that will be abundant. Right. So fine. We'll take it further. After isotopes, it is isobars. In the isotopes, atomic number is same, mass number is different. In case of isobars, atomic number will be different, mass will be same. If atomic number is different, then they become different elements also. That's why we should say the isobars are atoms of different elements with the same mass number, and different atomic numbers okay, with same mass number and different atomic number. So we'll take some examples. You can see here argon, potassium, calcium. Atomic number of argon is 18, 19, 20. They all exist in mass number 40. You can see the difference. Neutron number you can see. Atomic number is same. Atomic number is different. Mass number is same. So neutron number differs here. 40 minus 18, 22. And 40 minus 19, 21. And 20. You see? Okay. Fine. So atomic number is different. Mass number is same. Then they are isobars. We have one another called isotones. Then what are isotones? These are the atoms of different elements. But condition is with same neutron number. With same neutron number. Okay. So we'll take example. Okay. You can see this carbon 614 is there, no? Like that, nitrogen will be 715, oxygen 816. If you calculate neutron number, 14 minus 6 is equal to 8. And here 15 minus 7 is equal to 8. 16 minus 8 is 8. So all these are different atoms of different elements having same neutron number. They are called isotones. So come on, people have to tell me. Same atomic number, different mass number. What is that?
So isotopes.
Isotopes. Same neutron number,
So isotones.
Isotope.
same mass number, different atomic number.
Isobars.
Isobars.
1H1, 1H2, 1H3.
Isotopes.
Isotopes.
Isotopes. Argon, potassium, this calcium with mass number 40.
Isobar.
Isomer. So then it is isotope. So they may ask you which among the following combination is isotones, isotopes, like that in competitive exams also. Okay, so that's it. Fine. So after that we'll proceed. Now we'll speak about dual nature of light. Dual nature of light. See, light exhibits two characteristic properties. Which are the two characteristic properties of light? Anybody?
So reflection and refraction.
Sir, it travels in a straight line.
Okay, and apart from that,
Sir, it doesn't require a medium.
okay, then
It has no mass.
correct. Next,
Wave and particle. It travels as wave and
that
particle.
is wave nature and particle nature. Whatever other properties you people told, they are the consequence of wave and particle nature. Okay, dual nature of light. Okay, so light exhibits two characteristic properties. One is the wave nature. Another one is particle nature. See, any material particle having some mass will behave differently when we compare any energy form without mass. See, light is pure energy form. It doesn't have mass. When light is pure energy form having no mass, what we expect, it can behave like a wave. A wave, sound wave, for example. Okay, a heat wave, for example. They are pure energy forms. They doesn't have mass. They just have energy, that's all. And they move like a wave characteristic. Particle means a particle moves in a straight line. When it hits the object, it transfers the velocity or momentum. All these things are the characteristic property of a particle. But light doesn't have mass. It can behave like wave. That is acceptable. But light without mass can behave even like particle. That is what we say. It is dual in nature. It can behave like a wave and particle. So the experiments which prove wave nature is reflection, refraction, this kind of thing. And the experiment which proves particle nature is photoelectric effect. See, if a wave moves like this, a wave is always moving like crest and trough line. When it hits a target or object, it will reflect back. This is wave nature. Or it may refract back. Okay. So this is wave nature. If a particle goes, if it hits an object, it will stop there. Correct now? It doesn't move like a wave. A wave will reflect back, whereas a particle will not come back with the same velocity. So it will go and hit there and transfer the energy or momentum to the target. If the target is also a particle, then that particle starts moving. Correct now? So light exhibits both the properties. That's why it is said to be dual nature. That is the fantastic thing about light. Now, further we'll take it. If I say that light is a wave, light is a wave, then wave should have certain important properties. Okay, so characteristics of wave motion is of wave, or simply characteristics of a wave. When I say light is a wave must have to have certain important characteristics. Which are the characteristics or properties, you can say? So a wave will always have wavelength. Correct. A wave will always have wavelength represented by the symbol lambda. And wavelength, how do we represent? See, a wave itself is represented like this. If this is the direction of movement, a wave will move like a crust, trough, like. See, the maximum displacement above the mean position is crust. Below the mean position is trough. Okay. This is crust. And this is trough. Now, what is wavelength? The distance between any two adjacent crests, or distance between any two adjacent troughs, is what is wavelength. There are different radiations in the nature. Each radiation will have its own wavelength. Okay. Next, frequency. Frequency. Frequency simply means how often. How often is frequency, right? You would say, I always study in a day 10 times. Okay, so that is the frequency of study. I always eat sweets 20 times a day. Frequency. I'll go to movie 2 times a week. Frequency. So what is the frequency of the wave here? It is the number of waves. This is waves. One wave from here to here. Number of waves which cross a given point in 1 second. Okay. So number of waves, or lambda, that cross a given point. That cross a given point in 1 second is what is the wavelength. Frequency. Number of waves which cross a given point in 1 second is what is frequency. And wavelength has the unit. Unit of wavelength is meter or submultiples of meter. Submultiples of meter, when I say, like nanometer, 10 raised to minus 9 meter, picometer, like 10 raised to minus 12 meter, like that, kilometers, 10 raised to 3 meter. So it goes there. So generally, it is the distance. No, distance is having the unit meter. So nanometer, picometer, kilometer. Frequency. The unit of frequency is, okay, hertz. Basically, symbol is Hz, or they also measure as cycles per second. Cycles per second. Okay. Next we'll take third one. Third one. It is amplitude. A wave will have amplitude. Symbol A. What is amplitude? The maximum displacement of a crest or a trough. This maximum displacement of a crest or a trough. Yeah. Okay. This is the direction. So maximum displacement of a crest or a trough. About the mean position, you can add. Again, amplitude can be measured in the terms of displacement, that is distance itself. So submultiples of meters. Okay. So similarly, we can take up fourth one. A wave has its velocity. A wave will always be progressive in nature. It cannot be static. If a wave is moving like a crest trough like that, it is always progressive. It keeps moving. It doesn't stand at a particular position. So velocity. So it is nothing but distance traveled by the wave per second. Distance traveled by the wave in 1 second is what is velocity. And you take the velocity unit. Unit of velocity will be meter per second. Right. So also the final one, it is fifth one, wave number. A wave will have wave number. Wave number, it is nu. See how you write nu, frequency, right? You put a bar there, nu bar. So wave number is nothing but number of waves. Number of waves per unit length. Per unit length is means what, sir? Is it centimeter or meter? It depends on unit of measurement and expression. That's all. If you are expressing in terms of centimeter, number of waves per centimeter is what is wave number. Or if your unit of measurement is meter, number of waves per unit meter per 1 meter is what is wave number nu bar. So nu bar is always is equal to 1 by lambda. It's calculated as reciprocal of lambda. Therefore, what is the unit? 1 by meter is nothing but per meter or per centimeter, per nanometer, anything. Okay, that is wave. So when I say a wave, light is a wave. A wave should also have to have all these properties. A wave will have wavelength, frequency, amplitude, velocity, wave number. All these values should be there. And you should also know that in case of visible light, see what do you mean by in case of visible light? Then there are invisible radiations also. Of course, in the nature, there are plenty of invisible rays, and the rays which we can't see are more in number than the rays which we can see. Okay, the light, visible light, is a small portion of entire rays which are possible in the nature. Okay, so visible light is a small portion which our eyes can make sense of it. Okay, so visible light, in case of visible light, wavelength indicates color. Okay, red has its own wavelength, violet has its own wavelength, black has it has separate wavelength, like that. So visible light, when you take, okay, there will be a perfect wavelength for every color. Okay, light. Similarly, frequency would always indicate energy. Okay, frequency indicates energy in general. Frequency indicates energy of any radiation. Higher the frequency, greater will be the energy of radiation. Okay, so as frequency of radiation increases, its energy also increases. So that means we say cosmic rays in the universe have high frequency. So they are the most energetic radiations in the nature. Similarly, amplitude, A, indicates intensity. If some visible ray is highly intense, so that radiation has more amplitude. That's it. Okay, rest is fine. So just know about these characteristics. Next. Maxwell's electromagnetic radiation theory. Okay. Now, Maxwell has told any energy form, radiant energy, we say. Radiant energy means the energy which can be emitted or absorbed in the form of rays. Radiant energy, rays. So according to Mr. Maxwell, the radiant energy will have, all radiant energies will have an electric field component, an electric field component, and magnetic field component. and magnetic field component perpendicular to each other. Okay, they always will be perpendicular to each other and also perpendicular to propagation, direction of propagation of radiation. Propagation means movement, propagation of radiation. Radiation, that's the mean. That means you take any ray, according to Mr. Maxwell, that ray, if it is moving like this, if it is moving like this, then there will be a component of ray, a part of it which will be having magnetic nature, another part of it will be having electric nature. That's the mean. And these two now are perpendicular to each other. This is magnetic, this is electric, and they are even perpendicular to the direction of movement of ray. That's the mean. And they both oscillate so fast that rays will move with high velocities. Okay, these radiations are called electromagnetic radiations. So according to Maxwell, any radiation in the nature which is emitted or absorbed will be having electric field component and magnetic field component. That's why they are called electromagnetic radiations. Okay, so electromagnetic radiation. All electromagnetic radiations rays doesn't require medium for their propagation. They can move in air or vacuum. Okay, so we'll have same velocity, possess velocity. It is represented as c. The velocity of electromagnetic radiation is represented as c. In air or vacuum, it is 3 into 10 raised to 8 meter per second. Okay, in air or vacuum. Air or vacuum. So that's the concept of velocity and electromagnetic radiations. And according to Mr. Maxwell, radiant energy. Radiant energy means any energy which is there in the form of rays is continuously emitted or continuously absorbed by an object in the form of electromagnetic radiations always. Okay, that is the concept. You are going to study this electromagnetic radiations and the theory, everything in deeper level in physics. And as I told you, these are all the concepts which are required for us to understand Bohr's theory and its applications. Next we'll take up. Contrary to this, another scientist by name Max Planck quantum theory. Of radiation. Max Planck's quantum theory of radiation. According to Mr. Max Planck, light is not continuously emitted or absorbed. Okay, so then light is emitted or absorbed in terms of small packets of energy discontinuously. That's the meaning. Okay, discontinuously. Okay, that means radiant energy, we say. Okay, you have to understand the word radiant energy is emitted or absorbed in terms of small packets of energy called quantum. Plural is quanta, not quantums. This quanta is plural, quantum is singular. So small packets of energy called quantum. In case of light, particularly in case of light, it's called photon. Photon of light is. Photon is nothing but quantum in general. Any radiant energy means it may be heat energy, it may be light energy, it may be X-rays, all those things, right? Radiant energy. It will be emitted or absorbed in terms of small packets of energy called quantum. Okay, and only integer multiple of quantum will be emitted or absorbed. Okay, only integer multiple of quantum is emitted or absorbed by an object. Not fraction, that's the meaning. Any object cannot emit half of the packet. Integer multiple. Okay, so number that means energy emitted will be equal to integer n, a positive integer, you have to say, n into the quantum. Okay, right. So similarly, third possibility. Okay, energy present in each quantum is given by okay, E is equal to h nu. So this is it. E is equal to h nu. Remember this. I think one more point I just wanted to specify. I think I'm not specified here. Just remember this. I gave you this velocity, right? Velocity is for electromagnetic radiation. It is given by C. Velocity C is equal to product of wavelength and frequency. You should always remember. If you multiply wavelength and frequency of any radiation, it gives the velocity. So you can either calculate lambda or nu. So lambda is equal to C by nu, or frequency is equal to C by lambda. Anything. This is important. There will be problems on this also. 2 mark time. Okay, right. Based on that, you can see E is equal to h nu. No? Therefore, E is equal to, in the place of h nu, nu is nothing but C by lambda. But what is 1 by lambda? 1 by lambda is nothing but nu bar, wave number. So that is hc into nu bar. Also you can write. There are the different forms which you can use it for calculations. Sometimes energy of radiation will be asked to calculate. They would give wavelength or wave number or frequency. Based on that, accordingly you can use any required equation. Now, according to Max Planck, energy is emitted, radiant energy is emitted or absorbed by the source or object in the form of small packets of energy discontinuously, right? It is like a machine gun firing the bullets continuously, one after the other. Each bullet is one quantum, and firing the continuously, 20 to 30 bullets at a time is how exactly we can imagine a source can emit on it. Half of the bullet cannot be emitted. Only integer multiple of the bullets will be emitted. That's very similar analogy. Okay. So this is about now why these theories have been put forward. Each theory explains the different properties of radiation. The light radiation or any radiation will have particle nature, wave nature, and all these things. In order to explain the properties, different theories have been put forward. Okay. Just know about all these things. These are all required for understanding Bohr's theory and its applications. Fine. So this is Planck's quantum theory and Maxwell's electromagnetic radiation theory. Right. So we shall proceed further. So after this, we have something about the spectrum. Know about spectrum. Can anybody tell me what is spectrum basically?
Band of color.
Spectrum is band of colors.
Colored components.
Pardon me, color?
Colored components.
Color components, okay.
Range of frequencies.
Range of frequencies. Okay, next. Band of color, range of frequencies. Apart from that, That's all. Okay. How do you get spectrum? How spectrum can be obtained? How do you get spectrum?
By passing light through a prism.
Okay, what is that phenomenon called? By passing a light through prism, you get spectrum. That phenomenon is called what?
Dispersion of light.
Pardon me?
Dispersion.
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 Very good. So we can get spectrum by dispersion. Spectrum is the pattern of radiation in which different radiations are arranged in increasing or decreasing order of their wavelength, any one pattern. Okay. So for example, if you pass the prism, sunlight or white light or composite light, you say, okay, so a radiation, I need to make it narrow, so pass it through the slit, and then the light falls onto the prism and bends and gets separated also. Okay, so this is direction of light. You should show the arrow mark. This is white light or composite light, we say. It has all the different radiations of various wavelengths and frequencies, right? So, right. So this is prism. That is what is white light or composite light. Now, what you get, the radiation will have different radiations in a particular order. So, if you observe here, so different radiations will be there in light. So, what you get here is spectrum. Spectrum. So, what is therefore spectrum? It is the pattern of radiations. Due to internet slowdown, I am not able to write only. The pen is not listening to me. The pattern of radiations, the pattern of radiations obtained by arranging radiations in the increasing or decreasing also, decreasing order of wavelength. Okay, that's it. So the visible spectrum, example, visible VIB-GIR. Violet, indigo, blue, green, yellow, orange, red. From violet to red, wavelength increases. If wavelength increases, see, just now we had written C is equal to nu lambda, or lambda is equal to C by nu. What is C? Velocity of light, 3 into 10 raised to 8. It's a constant. Whenever you remove a constant, you can introduce a proportionality. So this is how. So lambda is proportional to 1 by lambda, nu. Okay. So when wavelength increases from violet to red, frequency decreases.
Decreases.
If frequency decreases, we say energy also decreases. So in visible spectrum VIB-GIR, which is least energetic, you can say red. Which is having more wavelength, again red. Which is more energetic, violet. Less wavelength, it is violet. Okay. So this is about the spectrum. The process of getting the spectrum by passing through the prism is what is called dispersion. This process, what is happening here is dispersion. Okay. So then we have electromagnetic spectrum. Electromagnetic spectrum. So what is the electromagnetic spectrum? As I told you, in the nature, there are different radiations. Majority of those radiations can't be seen by naked eye. And the part of electromagnetic spectrum in the nature can be visualized by the eye. So it makes sensation of vision when falls onto the eye. Okay. So if you arrange all electromagnetic radiations in the nature in the increasing order of their wavelength, then what you get is the entire range of electromagnetic spectrum. Okay. So arranging all electromagnetic radiations, EM rays in nature. Oh, I can't write only, man. In nature. Huh? Arranging all electromagnetic radiations in the nature in the increasing order of radiation will give electromagnetic spectrum. So which is the entire range? We'll see now. Okay. Now, you say you remember this entire electromagnetic spectrum through some name like this, R mu x gamma c, like that. Just as a name of a person, this is gamma c. From R mu x gamma c, you know, from R to C, each letter indicates a particular radiation in the electromagnetic spectrum. Here, wavelength decreases from R to C, so frequency increases. Energy also therefore increases. Oh.
So what is the letter before C?
One second, it crashed again, man. Today, I don't know, internet signal is too weak. It is not even allowing me to write properly. See, I have switched off my video also. These internet providers will promise 100 Mbps. It will not be even 15 Mbps. Can you see? Can you see the screen?
Yes, sir.
Okay. You're telling something. You tell me one.
Sir, before C, adenado letter.
Gamma. I'll write in detail. Look at this. What is this? Increasing order. We'll start from cosmic. Okay. So cosmic rays. After that, it is gamma. Gamma rays. Okay. After gamma rays, it is X-rays. Then what is U? Ultraviolet rays, UV rays. After UV, V represent what? Visible radiation. And after that, I represent what? Anybody? IR, infrared radiation. M represents microwaves.
Radio waves.
Oh God, I say microwaves. Okay, next, radio waves. Radio. From cosmic rays to radio waves, when you move, wavelength actually increases. But here I've written from R to C, R mu x gamma. If wavelength increases, frequency decreases, energy decreases. So, which is the most energetic radiation of the entire cosmos in the entire universe? It is cosmic rays.
Cosmic rays.
Which is the radiation with highest wavelength? Highest wavelength?
Radio waves.
Radio waves. Radio waves have a wavelength of the order of kilometers. One crest here, after 1 or 2 kilometers, another crest. Cosmic rays have wavelength of the order of picometers. Okay, 10 raised to minus 12 to femtometers, 10 raised to minus 15.
Sir, what is cosmic rays? How to generate it?
I didn't get you. Once again, clearly, loudly. Tell me once again. What if?
How to generate cosmic rays? And what is it?
You see, it is there in the nature. See, sunlight is the one which emits everything, all the radiation. It contains all different energy radiation, cosmic rays, and that can be subjected for dispersion to get different radiations in a particular order. Mechanically, how you generate a particular radiation, I think you have to consult your physics teacher. Otherwise, it is naturally there in the nature itself. Okay, naturally there in the nature. Fine. In this entire electromagnetic spectrum, a small portion of it is what is the visible spectrum, and what we can see by naked eye is the small range. That's all. And this small range is from around 400 nanometer to 750, 780, approximately. If you say 800 also, you can say, okay, around 780 nanometer. Because it is a continuous spectrum, you can't clearly demarcate the wavelengths. The moment UV radiation diminish, by the time visible radiation starts, by the time visible radiation diminish and IR radiation starts. So there is no clear demarcation. That's why the range, different books give different, 380 to 780 or 400 to 800 approximately they give that. So any radiation which has wavelength range between these two limits can be seen by naked eye. If it goes beyond this limit, then we will not be able to see. So the radiations which are there invisible in the nature is more. I think with whatever limited visibility, we can discover and innovate so much. If you can see all these X-rays, gamma rays, everything, I think there will be much more to explore in the nature. Correct? So this is about electromagnetic radiations. Fine, we'll proceed further. This spectrum are of different types. There is spectrum and its type. Basically, we can segregate them into two types of spectrum. One is emission spectrum. Emission spectrum. Another one is absorption spectrum. I'm not able to write only. The cursor is not moving at all. Emission or absorption spectrum. Now, what is emission spectrum? Again, spectrum means the pattern of radiation obtained by arranging radiations in the increasing order of the wavelength. What is emission spectrum? You take any substance, okay, and supply energy in the form of heat or electrical discharge or anything like that. When you supply heat, the substance gets excited, okay, then you stop supplying heat. By then the substance would have acquired some energy. It starts emitting the energy, okay. The emitted energy, when passed through the prism or any dispersive medium, then you get spectrum, okay. Now this spectrum contains different radiations arranged in the increasing order of their wavelength. Now how did we get this spectrum? By passing emitted energy through prism. That's why it is called emission spectrum. Emission spectrum. Is that okay? So emission spectrum is obtained by emitting the energy. How do you make a substance emit energy? Supply energy, it will absorb. After you stop the supplying energy, it starts re-emitting the energy. That is emission. Then absorption spectrum. During absorption also similar process you have to do, but how you get spectrum is slightly different. Now you are supplying heat, right? You may supply some 1000 joules. Entire 1000 joules of energy will not be absorbed by substance. A part of it will be absorbed by substance. Remaining part will be transmitted. Okay, this is transmitted, right? Transmitted energy. Entire energy will not be absorbed. See, for example, you are cooking the rice using a cooker. Whatever the amount of heat that is supplied will not be used only for cooking. A part of it will be utilized. Rest everything will be wasted as a dissipation energy. Heat will be dissipated into atmosphere or sound or anything like that. In the same way here, if it supplies 1000 joules, a part of it will be absorbed and remaining part will be emitted. When you pass this emitted light or emitted rays through prism and then get the spectrum, okay, this spectrum which is obtained by passing emitted rays through prism, it will have a kind of, let me explain like this. It will have a bright background like this, and in between there will be dark lines like this. There will be dark lines. So a bright background in between dark lines. What about these dark lines? These dark lines represent the absence of radiation of particular wavelength. If those dark lines were also having the radiations, then it would have become simply some continuous light radiation, that's all, without any discontinuity. So the dark lines represent absence of radiations of certain wavelength. Which are those radiations which are absent? That is the radiation which is absorbed by the substance here. So you are supplying some 1000 joules of energy, a part of energy will be absorbed, that whatever the amount of energy is absorbed by the substance, that is absent here. That dark line indicates absence of the energy. And transmitted light is passed through prism, and the rest bright background indicates the transmitted energy. And the dark line indicates energy absorbed by the substance. And that energy absorbed by the substance, when it starts emitting, it will give emission spectrum like this. So this is the emission spectrum and absorption spectrum. And in emission spectrum, in case of emission spectrum, okay, in case of emission spectrum, if it is, the substance that you have taken is element, or elements, okay, like hydrogen, oxygen, such kind of elements, then the emission spectrum for elements will have lines there, sharp lines, okay, in dark background actually. It will be having sharp lines like this, and background will be dark, and this is called line emission spectrum. Generally elements only will give this kind of thing. If you take any molecules or compounds like that, then emission will be band of colors. It will be a continuous spectrum. So something like this, like this. Different colors will be possible like that. This is emission, continuous emission spectrum. It is one wavelength, by the time it diminishes, another immediately starts. It is continuous spectrum. This is discontinuous, but this is also, both are emission spectrums. Okay, both are emission spectrums. Of course, only glimpse of it is required in chemistry. Just we need to understand hydrogen spectrum. Just know about it. So spectrum is of two types: emission spectrum, absorption spectrum. Now, how do you get emission spectrum? Take a substance and excite by heating or by supplying any amount of energy by any form. Then the absorbed energy will be re-emitted. That emitted energy, when passed through prism, then what you get is emission spectrum. Emission spectrum of molecules will have this kind of band spectrum. Emission spectrum of elements will be line spectrum. That is the difference. Now, when you supply energy, a part of it will be absorbed, remaining part will be transmitted. When you pass transmitted light through prism, then you get a spectrum. That spectrum will have dark lines in between. All these dark lines corresponds to the absorbed energy, and that is called absorption spectrum. So these are the different types of spectrums. Next, we'll take up probably Bohr's theory and its applications in the next class. Okay. So till then, take care. Bye bye. Time.
Thank you, sir.
Thank you.
Yes,
Thank you.
sir.
Yeah.
Thank you, sir.
I'll end the meeting. Thank you. Somebody is asking for recorded session. I'll see what can be done. Okay.